Okay, let's get started. So I will frame this as uh, my our frame here is that the field of data science is not just statistics. It can be reframed as computation with data, and as you know, computation encompasses so many different things. So all of these different fields, we believe, can come under the umbrella term of computation. So you have statistics, yes, but that's just one kind of computation. You also have modeling and model building, the visualization of the results of that model. You have machine learning, signal processing, image processing, semantic analysis, networks and graphs, um, different data formats, etc., etc. So you might think that you need specialist tools for each one of these, but what I want to show today is that Wolfram language really is complete enough such that it encompasses all of this and is very intuitive, and you can go from idea to execution very quickly. Okay, so as I said, this talk is composed of lots of different examples. Uh, I'll start with these kind of basic ones and then move to kind of more and more complicated examples. But these first two, um, it's really just showing how sometimes you might just use computation to count things. Okay, it's the most basic form of data science. It's unfortunately the data science that is most commonly employed by know people who work with data. Recently, there is a big focus on big data, but the complexity of the calculations haven't changed. So sometimes you are just counting, and that's what you care about. So we've got two examples here, text and images. The first one concerns the text in a well-known book, Lord of the Flies, where our first port of call is just to import the text of that book. This is in a TXT file that you should have access to along with the notebook. So I'm just going to import this. Um, and then I have some kind of helper functions here, which I'm just going to run. And these make a smooth histogram of the word frequency of three characters in this book. Okay, you have Jack, um, the the bad kid, if I remember correctly. You have the Beast, and then you have Ralph, who's our protagonist. And this is just to show, how the story evolves in the context of the word frequency of these three characters. And as you can see, we've just defined a function called plot name in order to do this, where the plot name function takes a name like Ralph or the Beast or Jack, and then some options. But these are just kind of styling options. Okay, so the visualization here is really quite intuitive. Everyone understands that the as the story changes in a book or a piece of text, then the frequency of words also changes. And here is a very easy way to represent this. Um, okay, as I said, this is just counting. If you wanted to go a bit further, you might start to have questions around the sentiment as the story goes on. Anyone who knows this story knows that things things don't go very well on this island. But perhaps we want some way of quantifying that. So we'll start with a very simple case. The objective is to find the sentence in the text with the most positive sentiment. Okay. In order to do that, we need to kind of extract the sentences first. So I'm going to do this, but I'm going to shorten the output because I don't want every sentence in my notebook. Okay, so this is a kind of a little bit of the first sentence, and then showing how many sentences we really have in this story. So I could also find the length of text sentences. You can see there's 5,768 sentences, and what we're doing here is taking the sentence that is maximal according to the positive sentiment, or specifically the probability of positive sentiment. All right, so this is the syntax. Maximal by just needs some data and a function. Okay, the sentences are our data. The function is this classification. And we'll get on to kind of more of machine learning classification later. But this is one of our built-in classifiers that classifies the sentiment of some text. And for those of you who haven't seen this before, this is kind of classic Wolfram language um, syntax, where this function could really be anything and this data can also really be anything. So it's quite agnostic to the input. So let's run this. It might take some time because it is kind of going through all 5,000 of these sentences and classifying each one and then taking the most positive sentence. There we go. Okay, so this is the sentence it found, and as you can see, this does seem like it would be very positive. Uh, Something I like to check often is you could use some more built-in functions that we have um, to find the position of this sentence within the story. So I assume that text sentences is structured like a list of sentences, in which case we need this. We want to find the position of this. As you can see, it's yeah, it's actually nearer the end than you might think. Okay. We can kind of double check we've got this right by taking the 3,971st part of text sentences and see that it's exactly the same sentence. So there's some basic computations on the data, but for those of you unfamiliar, hopefully this gives you some starting points. Um, cool, right. Now, that was just one sentence. Maybe we want to see how this sentiment evolves over time, just like we saw how the word occurrences evolved over time. So what we're going to do is classify each sentiment, sorry, each sentence by sentiment, and then give a score of 1 if it's positive, -1 if it's negative, and 0 if it's neutral or it just can't tell. The classifier can't tell whether this sentence is positive or negative. Um, okay, we're going to assign these scores and then kind of add them up as we go, and then you end up with some metric of sentiment as the story goes. Okay, and I've overlaid this onto the word frequency. So we can see you have the word frequencies of Jack, the Beast, and Ralph in black, red, and green, and then you have the sentiment in blue here in this more jagged kind of plot. And you might be able to make some kind of conclusions, like during the climax here, when the Beast is mentioned a lot, the sentiment is reasonably reasonably negative as the boys on this island are fighting and things like that. Cool. All right. I'm happy to answer any questions about this that you may have. Or if you want me to go through specific examples that are related to your kind of industry or your subject area, then I'm happy to do that too. This is a webinar for you guys at the end of the day. Okay, let's go through the image example now. Again, remember, this is all in the context of counting. It's just before we were counting words, and now maybe we're counting something else. Okay, so these are actually, I think, kind of nanoparticles being kind of injected into a substrate. I think this is a simulation of how this would happen if some kind of needle was injected into someone's skin. But yeah, lots of scientists doing work on this kind of thing. And you might want to actually be able to quantify what happens when you do, um, inject something into some kind of substrate. So yeah, we have these particles. We have an image. We have like a two-dimensional um, data structure, of pixels. But within that two-dimensional data structure of pixels, we have our particles, and maybe we want to kind of infer something about that. So what I go through here is a very small demo where it just takes two of these particles that are on here somewhere. I think it might be these two, and perform some computation on these. All right. It performs four different computations, as you can see from the four different kind of rows here, and displays them in a tab view. Okay, so I'm going to run this first. It runs very quickly because it's just on this very small kind of sub image. The original is just a resized image of this. Okay, we just use image resize, built-in function. Pretty easy. The second one uses a built-in function called delete small components, but uh, this is evaluated on a binarized version of this image. Okay, so binarized, what it does is it makes the pixels either 0 or 1, so white or black, and it decides which threshold to use automatically for that. And then delete small components just, um, well, it's the first example in the drop down here, replaces small connected components in a binary image with background pixels. Okay, so here white is considered the background pixel, so any small components are just set to the background, basically. So we've gone from this to this, and we're kind of getting close to something we can maybe measure. We know that we have two particles here, and we just perhaps want to find out where their centers are. So that's kind of linked to this next computation, where we work out a distance transform of the image, where the value of each pixel is replaced by its distance to the nearest background pixel, right? So those that are in the center, i.e. here, are furthest away from the background, so they will appear brightest in this distance transformed function. Okay, so we're getting really close now, right? Because the brightest point on these will be the kind of maxima or the center of each of these particles. And that's exactly what max detect does. Okay, so max detect essentially just gives us this point in the center of each. And we actually carry out dilation on this function where dilation gives the morphological dilation of image with respect to the structuring element. But in this case, it's just 3. So I think this is well, actually, I think this is the second example. But as always, I have the documentation here so I can find out exactly what it's doing in there. Okay, so the workflow is relatively simple. If I want, I can just click this cell and then my code disappears, but I can always get it back if I click this. And then I have this nice tab view interface where I can click through the different images. But more importantly, we can generalize this to the whole image. Okay, do the same computations, but this time on every single particle in the image. And instead of just showing the max there, we've actually overlaid these white crosses on top of the particles in the original image. Okay, and once you've got these positions, as I said, in this two-dimensional matrix of pixels, we've essentially got coordinates, and we can plot the density of those particles using smooth histogram 3D. Okay, so we can see this kind of two overdense regions, um, perhaps suggesting that as these particles have been injected, they kind of go two different ways um, into this substrate. Cool. All right. I think I have some questions here. Someone asks, why is there a connecting line between the two centers? Um, oh, in the distance transform one. Yeah, good question. So what that's saying really is that this point here is close to the background. Okay, so as you can see, this is closer to the background because this is all background than this is. So yes, I think that's what's going on there. I mean, you can kind of see a similar effect in some of these like radial spikes. Perhaps these particles are kind of a bit oblate, so they're kind of squashed. Therefore, this line is kind of the closest to the background than any other radial line from the center. But yeah, that's a good question. Um, this is my whole point actually. So a good question uh, about seeing what we can extract from the data. And some of these questions I may have to answer separately by email or something like that. But yeah, keep them coming. Uh, I will try to answer them to the best of my ability. Okay, so I mentioned there just kind of injecting a new viewpoint and a new and some context. These are themes that come up in this talk, right? So we've got a couple more examples here where the objective is to inject context into our data, right? Because some data is just not interpretable at all. Uh, you need this context to make the data make sense. All right. So the example concerns some shipwrecks, like a data set of shipwrecks, which here I'm importing as a tabular object. Uh, you can see we've got the name of the ship, the date on which it sank, a description of the ship, and then the coordinates of where it was last seen. And if it sunk, then where it was last seen is really where it is. Okay, just at a lower depth. Okay, we can take this tabular object and convert it to data set, showing you how we have different ways of handling data in Wolfram language. Tabular is new. It came in version 14.2. We now have version 14.3, which was actually released today. Um, Anyone has any questions about that, I'll be happy to answer too. Okay, yeah. I'm going to use the data set here just because it's, well, it doesn't really matter to be honest, but that's just how I've written the code. Um, all right, so we can make a word cloud from all of the descriptions. That's all of these rows. Uh, that gives you an idea of the type of ships we're dealing with. It might mention some countries that were involved in the battles that led to a ship sinking. Yeah, okay. We also have a list of dates here. Now, one thing I wonder, if we were to, let's say, just extract a couple of these dates, then I might use something like rex ds. So this gets me the first three rows. Okay, and these are the first three sunk dates. And I'm just going to use normal of this, which kind of um, takes it out of the dataset wrapper. Okay, and gives us just a list. Um, so as you can see, these are kind of formatted in quite an interesting way, where these are actually what we call date objects in Wolfram language. So these are very meaningful symbolic objects that represent dates that we can kind of plug in to um, other computations. So we actually have just got this new function called mid-date, or maybe we got it last version. It gives the midpoint instant of a date or a list of dates. So I believe we can give it a list of dates, and it will give us the mid date. Okay, so there we go. As I said, agnostic functions. Um, all this needed was a list of dates, and that's what I gave it by using percent, which just means my last output cell. Great. Okay. Now, what that means is that we can readily plot a date histogram of these dates because date histogram needs dates, and that's what we have. Okay, as you can see, the data is incredibly dense around the year, basically around World War II. Okay, so we've got to keep this in mind. If we thought this was an investigation of all shipwrecks, you know, without keeping in mind that we kind of need to do some normalization somewhere because, you know, the data set is just overwhelmingly filled with World War II shipwrecks. Okay, so we can plot all of these coordinates on a map using GeoListPlot. You could even imagine, adding some kind of slider here where you you kind of showed the coordinates with time using something like manipulate. So this is one of our um, very well-known built-in functions that is incredibly useful for showing how expressions vary as you change one of the parameters. So yeah, I could imagine something like you have the date as a slider, and then you have the coordinates as they appear on the map. As you can see, these shipwrecks, it doesn't seem to include any that occurred in the kind of Eastern Hemisphere. So it's also something to keep in mind. And GeoListPlot has automatically figured that out. Okay, we don't need the whole world map to see all of these points. We just need this kind of bounding box that we're interested in here. Okay, in a similar vein, we can do a geosmooth histogram, and this is because of the overwhelming amount of World War II data. It hasn't even registered these points down here. So again, this is all things to keep in mind. Maybe the geosmooth histogram is just not that appropriate in this case um, because of the incredibly high density around this area. But as with most things in Wolfram language, you can probably, well, I won't say probably, you can definitely kind of configure this such that it 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 would um, it would include these points. Um, it just doesn't in the default setting. I have a question here about the word cloud being in Arabic instead, and yes, I'm sure that that could be arranged. So if you did, well, we have lots of language-oriented functions. So here, this one can identify the language that a string is probably in. Um, word translation gives translations for word into the language specified by lang here. So um, I'm actually quite interested in seeing what this looks like because, well, because you asked the question. Um, so I'll copy this example from the documentation. Uh, show you what it looks like in this case. Okay, so here we had to say from English to another language. Sorry. Uh, okay, so I'm just going to get the entity for the Arabic language. All right. Okay. So word translation of some string, which I'm going to indicate just with a slot for now. And I put my ampersand on here indicating that this is a pure function. This is now technically a function that can be mapped over any um, string or list of strings and then give us the Arabic um, translation. All right. So if we look at the output of delete stop words, we have this list of words. Um, I think this has still been string joined, so I'm just going to delete this output here and check that this is a string by asking for the head, and it is a string. So I don't think I want to string join it, so I'm just going to say um, yeah, this can take a list. So oh, I got this right. Ah, one extra comma. Okay, so if I do normal here, and then we have this, we have a list. All right, great. So with this list, we can delete the stop words, and then technically um, find this as list, suppress the output. We can map this over our list. Now I'm just going to do the first 5 elements of list because uh, oh, okay. Now I suspect that because there's lots of place names here, there isn't the translation. But let me just try something instead. So like dog, cat. Okay. So it does work. I think the translations weren't available for these all these place names and these kind of um, shorthand for U-boats and things like that. But um, yes, you can still make word clouds of different languages. Oh, interesting aside there. Right. Someone has asked about, can geolist plot do coordinate projection, i.e., from geodetic coordinates to UTM? Yes, it can. Um, so we actually have a whole other webinar on this if you look out for geographics with Wolfram language. But I'm in the documentation of GeoList plot here, and if I go into the details and options, um, what is it here? Okay, yeah, I'm just going to scroll down into the scope. In fact, yeah, because this is GeoList plot, so this is kind of a data-oriented uh, function. I'd rather go into geographics. I think that's more likely to be where it is. Yes, sorry about that. So this is more of our like base level geographics function. So any kind of projection options will be here. They will be able to be used in all of these other geoplotting functions, but this is where there'll be the information on them. So as you can see here, projection is one of the options of geographics. And if I click this arrow, it will take me to examples that use geoprojection. And here, for example, you've got a different geoprojection than we usually see. And I can go into geoprojection itself to find all of the different geoprojections that we support. Okay, so yes, hopefully this answers the question that you had. Okay, so we're not quite done with this example. The next thing is to incorporate some elevation data under the sea in a certain region. So what I'm going to do here is essentially just make a box around where most of the data is, and this is a kind of um, well, what is it? Like latitude longitude box. Yes, latitude longitude. Okay. Um, so geoposition needs a list of the latitude and longitude, and here I am kind of finding all of the data in our well in this latitude longitude region. So first, what this is quite a simple function, but I'm making a table of all of the geopositions um, in this region, and I think it automatically will to every kind of 1 degree of latitude and longitude. That's what this is doing. I can indent my code a little nicer so you can actually see. Now, some of you may know you don't have to indent your code in Wolfram language, but sometimes it helps for readability. This is a language designed to be read by humans after all. Okay, so then we want the geo elevation data at every point within this box array. All right, let's just, there you go, there's some geo positions. This is the geopositions for which we're finding the elevation data. Okay, this might take. Fortunately, I think there's been a kind of corruption of one of the libraries that um, finds this. I don't know why, because it was working before, but thankfully I have kind of way around this because I have this iconized box of this C data that I've just saved in the notebook. Okay, so this works fine, and we can continue with the example. Okay, so we have a function that returns the depth at a given location, which will be useful here. Um, and then we have another function which returns a point if the geolocation provided lies within this view box. Okay, so you can see it takes a geoposition. Okay, and then if it's a member of our box, then we get the point, and if it's not, then we don't. Okay, this is just some function that gets the plot of the shipwrecks as well as the geo elevation data in the sea. You can see here we've done a kind of select the rows within the Rex DS where we don't have missing coordinates. Okay, and then I've left a link here to the function transform missing, which is a tabular related function where you can kind of decide what happens for missing data points in your tabular data. So that's quite useful. Um, okay, yeah, so we've already run this. And finally, we can see first we can plot a histogram of the depths. You can see the most common depth is actually still quite close to the surface. So this could be ships that, ran aground near the shore. But then here's, I think, what we're most interested in is a 3D visualization of all shipwrecks within the view box. All right, so this is using our geo elevation data. And here we go. So this is a 3D graphics object that we can move around. And every time we have a blue, no, I guess it's a black point, that's a location of one of the shipwrecks. And as you can see, every time I let go, you get these latitude, longitude labels. So I can just include these labels. In my graphics. Latitude. Just ignore these functions that are coming up because I do just want it to be a string. And then I might need to do axis goes to true before I use axis label. I'm not really sure why that's not working. Perhaps if I put it here. Okay, there you go. So I think what was happening there is that because we're using show, we're like essentially showing several graphics combined, where if this list plot 3D didn't have axis labels and this one did, it was kind of overriding. So if we put it in the options for show, which takes the same options as graphics, we're fine. And then we have the axis labels here. Okay, nice. Okay. So there are some other examples here. One of them is related to the food hygiene scores that are given out to anywhere that serves food. Uh, I will just let you look at that one yourself because I'd rather move on to some other examples. Uh, for example, this one shows accidents in London taken from I believe, a kind of open database from uh, like the crime statistics in the UK kind of thing, where this is kind of how it looks like when it's imported in this data set. We have the geoposition, the date, the severity, and then the vehicles that were involved. Um, okay, we can focus on how this data looks in a kind of specific location, and then explore the density. I believe this is just our point of interest, and then look kind of look elsewhere in other areas to kind of expand our search scope here. You can see the code that generated this just by clicking this here, but I think it takes quite a while to run. So there is one feature that wanted to show now. This is 14.3, but you can do kind of styling on your tabular columns using something like this. And what this does is it colors every first column blue, every second column kind of green, this kind of green, and then every third column purple. And this cyclic function kind of does what you might expect, is that it cycles through um, the future kind of potential things that are in this list, right? Because this list obviously only has three elements, so you might ask, what is the fourth element of it? Well, it cycles back again, so it's blue, right? Yeah, it's kind of a tiny little feature, but I wanted to show it anyway. Yes, as I said, I'm on version version 14.3, which is brand new. Okay, so let's move on. This is another example where I probably won't spend too much time. I'll let you kind of click through this, but I'll just show you what's available here. Uh, this is from one of the consulting projects that we did here at Wolfram, where we were tasked with exploring the data surrounding a supersonic car. Okay, as it you know completed its drive cycle and went supersonic, and then eventually deployed a kind of parachute to slow down. And we have all kinds of pieces of information here, like the RPM and the suspension load, and um, you might just want to visualize that. You might want to um, apply some calculus so you can visualize the velocity and the acceleration, as well as the throttle that's being, that the driver is inputting. This is an example of a kind of flip view where I'm just clicking through and I get different plots each time. Signal processing, this is something that I mentioned in my kind of word cloud earlier, is that you can go from a plot like this, where you have like the load on the front left wheel, to a more kind of signal based, kind of frequency based plot. Um, I think this comes from this function maybe, um, or wavelet scalegram. Yeah. So as you can see, incredibly high level built-in function plots the transform coefficients as rows. Um, to show like what's happening to different frequencies as this car is driving. Okay, uh, and when you're showing this to your client, they now have multiple different viewpoints to um, they can use to kind of face this problem. Great. Okay. Similar kind of example here where we have an audio file that if I press play here, you should be able to hear. Sorry if that was too loud. But yeah, what this represents is a car essentially going past a speed detector and ultimately getting a speeding ticket. So that's just the audio file. You can hear classic Doppler effect happening there. We can use this spectrogram function to kind of um, well plot the spectrogram and see what this see what kind of frequencies are like we're dealing with here. Okay, a spectrogram is also known as a time frequency plot. Shows how the frequency content of a signal changes over time, that kind of thing. You can explore the very technical details down here. Um, we also have a kind of built-in pitch recognizer, which may well be calling a kind of built-in neural net, which is specially trained to recognize pitch. Yeah, yeah, exactly. So here, as you can see, the possible settings for the method include uh, CREP here, which is a neural network trained for pitch estimation. Um, and then these are not, I don't think, neural net based, but um, this one certainly is, and I think that's the one we use here. Okay, so we've got pitch recognized. I mean, I know there's very different things, but when you've been programming in Wolfram language as regularly as I have, you start to see something like pitch recognized the same way as you see like classifying by sentiment. It's all kind of the same thing. It's all doing some kind of machine learning under the hood and classifying it according to um, some metric. Whether that's sentiment or in this case a bit more quantitative is the pitch. All right. So this is our time series of frequency data. So literally how the frequency of the signal in this 5-second audio file varies over time. Okay, we can use dateless plot, which is kind of yes, it says date here, and these aren't necessarily dates, but you know, a time in seconds is essentially just a very short date interval. I could I could just use list plot, and then it wouldn't join it up, and that would be fine too. Okay. And then we want formula for the relative velocity as the car passes by the observer. In this case, it might be the person in the police car doing the speed detecting, or maybe the observer in this case is just some kind of speed camera. Uh, and then we want the Doppler shift formula. I do think you could probably get this a different way using something like formula. look up. Um, yeah. Okay. So this queries our internal formula database and finds every formula containing the word Doppler. Uh, which one do we want here? Guess it's this. So once you've got the one you think you need, you can then use formula data and you just input that and then you get the formula. So this is exactly the one we've reproduced here. Um, so that's good. Okay, so it yeah, it doesn't really matter, but I like to use our internal tools where possible. So okay, so we've got these two formulae. Uh, we want to build a model that we will fit this frequency data to. So this is going to be our model where we have the Doppler shift that's a function of frequency. Uh, we're going to say we have a zero um, observer velocity. We have a stationary observer. Um, the speed of the car is given by uh, this relative velocity, which is in terms of um, the distance to the observer and the speed that the car is going, and well, the time as the time passes. Okay, and then the speed of sound, we've just used the um, speed of sound, which is actually a unit. So quantity one speed of sound gives us one speed of sound. But if we kind of do unit convert I wonder what this get. Okay, unit convert has actually automatically chosen the unit of meters per second. So one speed of sound is 340 meters per second. It's a bit like how gravitational constant g as the unit of g's. It's this like if I do quantity magnitude of this, I think it will just give me one. Yeah, because it's one Newtonian gravitational constant, even though that unit is obviously expressible in, you know, Newton meter squared kilogram to the minus two. While we're here, we might as well just test that. There you go. 6.67 times 10 to the minus 11. Anyway, I always get a bit off track here. Rudolph has asked, do we have the sound of the car in the downloadable notebook? Yes, you do. You have this audio file. It's saved in the notebook, so you can do your own analysis with this if you like. Okay, so let's just evaluate this, and we have our model that is yet to be fitted to the data, but this is what it looks like. And then we can use nonlinear model fit with our frequency data to our sound model. Here we're just saying we're going to guess the value of f. We're going to start searching at 350 hertz. Okay, this is our fitted model. We're going to see how good it is. And there you go. It does a pretty good job. And finally, we can find the best fit parameters. So this is the actual uh, frequency. This is the distance to the observer. So only 5 meters away. So, I don't know in which direction that was, whether this was a speed camera on a bridge that was 5 meters high or whether it was a car that was 5 meters off the side of the road. It's it's open to interpretation. Maybe if you had more data, you could actually find this out. Uh, this is the velocity in meters per second the car was going at the time of closest approach, and this is the time at closest approach. Great. Uh, I think it would be a shame if I didn't mention these new functions we have, one of which is list fit plot, which which after this talk is finished, I might actually come back and just make simplify the code slightly with using some of these brand new and 14.3 functions. So this plots a fit curve for you without having to, you know, show using the data and then a plot on the top. Okay. Um, yes. Now this was a kind of special case where we explicitly like gave the formula and um, fit the model to some no, yeah, fit the model to some data. A list fit plot, it gives kind of local regression lines. You can also specify if you want a linear fit or a um, here you go, linear fit or a exponential fit should be somewhere. I suppose I could just look in the options, plot fit. There you go. It can be automatic, it can be linear, it can be quadratic. As you can see, it can be all of these things too. We could also use plot fit elements goes to band curves and actually see the well, these are essentially the residuals of your fit with your data. Great. So you've seen the workflow. Perhaps though, you just want to present your findings to, I don't know if it's your boss or your students or your tutor or something. That's where this nice tab view comes in, and we can actually just organize our workflow into this nice tab view where here's our audio file and um, here's kind of the method we use. We use this neural network. We have our Doppler model, and these are the results. Yeah. If anyone has any questions on this, I'm happy to answer. Also, I should say that your questions come to the moderator first. They don't just go straight out and for everyone to see. So, okay, this is kind of a fun example. Um, so in the initialization, we kind of unzip a file of images, and all of these images are of different types of dogs. Okay, there we go. Going to delete this to keep my notebook not getting too big. Um, the first thing to do here is make a feature space plot to essentially see how similar and different these images of dogs are. And I've actually used a brand new function labeling target here, which is new in 14.3, and it specifies essentially how we're instructing um, our feature space plot to be labeled. So you can say all, you can say none, you can say you want some fraction of the items to be labeled. So if I just say 0.4, then it should be that some of these dogs lost their labels, but I'm not sure. Maybe this is only with where the data is sufficiently dense. I mean, you should play around with this for the kind of standard feature space plot cases. Perhaps it's not having too much of a large effect on this data, but yes. Anyway, besides the point. If you hover over these, you can see that you can just see bigger versions of each image too. All right, and we're going to create a nearest function which takes in this data set and um, this essentially provides us with a thing to compare all other photos of dogs to, right? So then we have another data set of test images of dogs, and we're going to see which image in this dog data set is closest to the image of the test dog data set. All right, so that should, so you can see these are all the test images, and these are the ones that the um, nearest function found was closest to. So as you can see, it does a pretty good job, and some of these may even be the same dog. Like I suspect that yes, this is exactly the same dog. It's just one instance is in the input data, and one is in the output. Okay, and this is kind of like unsupervised machine learning, right? Where you just show how this data is distributed, and it's unlabeled, but you kind of algorithmically determine which category each piece of data should be in. And as you can see, the feature space plot does a pretty good job of differentiating the three types of dogs listed here. We can also use feature space plot 3D to kind of give an extra degree of freedom in which to position these in feature space. But as you can see, you again get the three categories. But because the three categories were found in 2D, you kind of don't really need to do this. But it is a really nice rendering, and you can see that just like how using our graphics functionality, you would position like you can put a rectangle in a 3D graphic and it still looks 2D. Okay. Um, that's exactly what it's done here with the images. Huh. Someone also asked whether find formula can find the Doppler model. It's a good question. Um, I'm not sure. That's something to play around with. Uh, if you find out, you can let us all know. So find formula finds a pure function that approximates the data that is input to it. So there's some examples in here, probably some basic examples where um, well, not very basic actually. So they've taken a sum of a sine and a cosine and then added some noise, and then this is the result. And then as you can see, find formula has kind of identified some sums of sines and cosines that it thinks is the right formula. I mean, I really want to test this now. Sorry. So I'd probably just use my frequency data and I just use find formula. I'm not very hopeful here, but why not try? Yeah. So it's instead decided that this is more likely to be approximated using a kind of cubic polynomial. Um, and I mean, we can what would we do? I would probably first make a table of x and then f of x as x goes from 1 to 5. I'm just going to say in steps of like 0.1. Okay, and then just list plot this. Yeah, so it doesn't do a very good job, but we don't know until we test. Yeah, I think I kind of skipped an example here. This is a more kind of classic machine learning example, but I've got some really good questions, so I'm going to focus on those for a bit. Someone said, elaborate further on what is the XY dimensions of, I think you're talking about this feature space plot, right? Um, so show this again. Let's first go into the documentation of feature space plot. So what it says here is it plots the features it extracts from the examples as a scatter plot. So imagine you're thinking as a computer thinks here. You have all these images which are just RGB values of pixels, right? Uh, and you want to extract some features of that of these. So you know we can kind of see the features that a computer extracts when a computer sees an image of a dog. We can't really see that when humans do it. We kind of see a dog and we just have some sense that yes, that's a dog. Um, so it's those kind of hidden features that um, that it's extracting. Okay. Yes. Here's a really nice example in the documentation, right? So what we do is rasterize the letters in the alphabet and then feature space plot them. And you can see that letters that kind of look similar are close together, like I and J here. But the coordinates of this plot isn't really meaningful. It's more just like things that are deemed to be similar about these pieces of input data. Okay, so I hope that answers your question. I mean, I've been thinking about this a lot recently. If you think about some of the new video generative models like VO3, they've been able to extract the the features that are relevant to some really complicated like video, like fluids flowing, like, or something like that, or like, these things are really hard to program, but with the ingestion of enough data, these kind of generative models have been able to kind of capture it and, and replicate it. Would it be possible to ask Mathematica to tell us what compute metrics algorithms it took to compute the spatial clustering? Yeah, really good question. In fact, yes. So I can tell you're very interested in this, and for you, it is it is in the details and options. It probably should be a bit higher up because you have lots of styling options and things like that. But if we really care about what's going on here, we're interested in this method section. So the method that they've used, or that the Wolfram kernel has used for this feature space plot, can be one of these things. Okay, so latent semantic analysis, linear low rank matrix factorization, TSNE, that's quite a common one, or principal components analysis. So I suppose to answer your question, um, you can set these explicitly. Uh, and there's probably a way to of like just running it and then seeing what method it used. But let's um, let's just try one of these. So if I say method goes to, oh, as you can see, they all come up here. So I can just say principal components analysis, and then it's running. Okay, so very different result. Uh, and I think you can still broadly see three groups, but it's definitely not as clear. So this the automatic choice of method is probably doing some kind of ranking and finding out which method it thinks is performed the best. Um, yeah, so I suppose you could try this example with each method, and then you'd be able to find out which method was used automatically. So yeah, thank you. There's a short section on app deployment here, um, where it uses the City Bikes API to find the availability of bicycles in pretty much every city that has them. So this is really quite cool. So the code to do this is accessible using this just clicking the cell here. You can see it's not that much code. It's a dynamic module which kind of um, essentially hits this API at this URL, and it just needs a city as input, and it's letting us kind of pick this city, um, you know, pick it ourselves, and then essentially just doing an import of that URL, like importing the data directly from the URL, which you can do in this um, in Wolfram language. So let's choose Barcelona. I'll give it a second to load. As you can see, that it has to go and fetch this data from um, the API. So, excellent example. So we've got now our dashboard, which shows us the availability of bikes in Barcelona, where you've got a legend here, and what it looks like is that all of these kind of bike storage locations are empty, but then some of these are full of bikes. Or at least that's my interpretation. Yeah, so number of bikes over the number of bikes plus the number of bikes that are free. It could be the other way around. But this is a really nice kind of interface and very simple to make. And then the cool part is that we can just use this cloud deploy function and set the permissions to public to deploy this app onto the Wolfram cloud. And then we have a kind of cloud-based version of it that you can just send to a friend, and they don't even need to know any Wolfram language to use this app that you've made. Um, yeah, great. So we see that this app used the City Bikes API, but we can also kind of create our own APIs and deploy them. Where this example uses a classifier function that is built in this example using Titanic data. Now, I don't think I'll have time to go through all of it, but if you go through this example yourself, and you'll kind of see the result, and then you can this API deployment will make a lot more sense. It essentially just deploys an API function that um, queries the database. No, not database. It calls a classifier function that's based on Titanic data of who survived and who died, right? And then you just use URL execute um, and specify, which class someone was in, what age they are, and what sex they are, and then you can see whether they survived or whether they would died, or whether they be predicted to survive or die on the Titanic. One final question here. Sorry. Yeah, I'll just answer that privately. Okay, so about reaching the end of the examples, there are some key points that I want you to take home. Is that this tool set that we have um, with Wolfram language is huge. Okay, um, a very nice way to find out how many built-in functions we have at any one time is to just use this. There are over 6,600 built-in functions. Okay, um, automation, as you can see, as you've seen in this webinar, there are lots of cases where automation is used. Okay, we have built-in classifiers, we have built-in neural networks which do pitch recognition. Okay, that makes the tool set more accessible. Also, the agnostic nature of the functions makes the toolset more accessible because you can just plot, spectrograms and you know, periodograms, um, and you don't have to massage the data into a really specific sequence of arguments to do that. Oftentimes, these functions just take one thing that is a list of the data you're interested in. So um, the language has been really carefully designed um, to make this tool set more accessible to us and to encourage the human to actually ask deeper questions of the data and use your domain expertise to um, actually reach conclusions.